Hey everyone, and welcome to this explainer. Okay, so today we're going to completely cure your struggles with pharmacology. I know, big promise, right? But we're going to do it using some really high-energy, high-contrast visual learning. We're going to take concepts that normally seem incredibly dense and just break them down so completely that you'll literally never forget them. Let's get into the chapter of the confused neuron and tackle pharmacokinetics.
So, to kick things off, let's introduce our mascot for today. Check out this little guy right here. This is the confused neuron. And, well, you can tell he is currently completely overwhelmed by the complexities of the nervous system and drug mechanics. I mean, he's stressed, he's anxious, and he basically has absolutely no idea how medications actually travel through the body.
You know, Charles Dickens once wrote, "It was the winter of despair." And let's be real for a second. Nothing says winter of despair quite like sitting down and studying pharmacology for your final exams. It can feel like absolute torture, right? But seriously, don't worry. I promise that by the end of our time together today, understanding this topic is going to be as easy as slicing a sharp knife right through warm butter.
All right, first things first. We need to draw a hard line right out of the gate between our two main concepts here. Take a look at this comparison. On one hand, we have pharmacokinetics, which is what your body does to the drug. On the other hand, there's pharmacodynamics, which is what the drug does to your body. A great trick is to think of kinetics as motion. You know how your body handles the drug, moves it around, and eventually gets rid of it. And today, we are putting our blinders on and focusing entirely on kinetics.
Now, this chart brilliantly illustrates the rigorous academic journey a drug takes. This is straight from the pages of the renowned Lippincott Illustrated Reviews, and you can see the whole complex flow here. It goes from the dosage requirement, through absorption into the plasma, all the way down to the drug's effect at the site of action. It's a fantastic reference for sure, but it kinda looks a bit dense and intimidating, doesn't it?
So, let's just ditch the whole pathetic monotone PowerPoint presentation vibe. We are going to energetically introduce our core mnemonic roadmap for pharmacokinetics instead. Look at these 4 steps. We call it ADME, or as I actually like to think of it, Adam spelled funny. A is for absorption, D is for distribution, M is for metabolism, and E is for elimination. Honestly, if you remember ADME, you basically know pharmacokinetics.
Okay, moving right along to step 1. A is for absorption, which means crossing the membrane.
This step is all about the physical act of getting the drug from the outside world into your vascular system. The absolute crucial point to understand here is that for a drug to technically be considered absorbed, it absolutely 100% must pass through a barrier or a membrane. Think about swallowing a pill. It has to actually cross the membrane of your gut. Or taking a puff from an inhaler. It has to cross the thin membrane of your lungs. Bottom line, if it doesn't cross a membrane, it's not absorption.
Now, I'm going to hit you with a rapid-fire rhetorical question that honestly trips up almost every single medical student on their very first day. Does an intravenous or IV drug have the fastest absorption rate? I mean, think about it for a second. It goes straight into the vein, so it's got to be the fastest, right?
No way! Emphatically no. Intravenous medications are injected directly into your bloodstream. They do not cross any membranes at all, which means they bypass absorption entirely. They literally have zero absorption phase. And because of this sneaky little technicality, inhalational drugs, which instantly cross that massive surface area of the membranes in your lungs, actually have the fastest absorption rate. Boom, consider that trap completely avoided.
Let's look at part 2. D is for distribution, going from the blood to the tissue. Right, so this is where we take the drug out of the blood and deliver it into the actual target tissues, like our poor confused neuron from earlier. To really understand distribution, we have to contrast 2 major types of drugs. First up, water-soluble, or polar drugs. Since your blood plasma is mostly water, these guys just float freely and happily in the bloodstream. But here's the catch. Cell membranes are made of lipids, which are fats. So water-soluble drugs bounce right off that membrane. Access denied. On the flip side, we have lipid-soluble, or non-polar drugs. These guys absolutely hate water. They actually have to hitch a ride on a protein carrier, like albumin, just to travel through the bloodstream. But once they reach that lipid cell membrane,
Oh yeah, they cross it like a sharp knife through warm butter. Because, well, lipid mixes with lipid perfectly. That is an incredibly powerful analogy, so definitely file that one away in your memory. Lipid-soluble drugs basically have the ultimate VIP pass to enter your cells.
So, let's see exactly how they use that superpower when they encounter the blood-brain barrier.
If you notice those astrocyte foot processes wrapping so tightly around the brain capillary, that whole barrier is meticulously designed to keep toxins out of the brain. A water-soluble drug, it gets blocked immediately. But a highly lipid-soluble drug, it uses that warm butter superpower we just talked about to sneak right past those astrocyte foot processes, finally reaching our confused neuron deep inside the central nervous system.
Moving to step 3. M is for metabolism, also known as biotransformation.
Okay, so what exactly is biotransformation? Put simply, it's the liver converting an active, working drug into an inactive piece of trash. Once a drug, say acetaminophen, has done its job and cured your fever, it needs to be turned off. The liver steps in, chops it up, and prepares it for disposal. Now, I will say, the liver is kind of like a mad scientist. Sometimes it will actually take an inactive prodrug and turn it on, or it might accidentally create a toxic metabolite, but its main day-to-day job is turning the active drug into inactive waste.
And finally, step 4. E is for elimination, or simply taking out the trash. Let's meet the absolute heroes of the elimination phase, your kidneys. The vast majority of drugs are filtered straight through the kidneys and then safely excreted from your body in your urine.
But wait, the kidneys aren't the only exit doors. Let's quickly rattle through all the different routes a drug can actually take to escape the body once it's done. You have the kidneys making urine, obviously. Then you have the biliary system dumping waste into bile, which leaves through the intestines as stool. Wildly enough, you can literally excrete certain drugs in your sweat. And you can even eliminate volatile drugs through your lungs and your breath. Just think about how a breathalyzer detects alcohol. That's pulmonary elimination in action.
All right, before we totally wrap up this section, I just have to inject a bit of classic medical student survival humor. If you are ever on clinical rounds and an attending physician aggressively pimps you on the side effects of a drug you've literally never heard of in your life, just confidently say nausea, vomiting, and diarrhea. Because drugs and their elimination pathways mess with the GI tract so much, guessing NVD will make you right about 99% of the time. It is truly the ultimate get-out-of-jail-free card.
And would you look at that? You have successfully unconfused the neuron. Look at him, he's actually smiling. We have followed the entire physical journey of a drug through the body, and you've just conquered the absolute foundation of pharmacokinetics. You know your ADME inside and out: absorption, distribution, metabolism, and elimination.
But I do want to end today on a final, somewhat provocative thought. If your liver is incredibly busy metabolizing one drug, what on earth happens if you introduce a second drug into your body that relies on those exact same liver enzymes to be broken down? Does the traffic just jam up? Does the drug stay active longer and suddenly become dangerously toxic? Think about that drug-to-drug interaction, because that is exactly what we are going to dive into next time when we explore liver enzyme inducers and inhibitors. Keep that curiosity alive, and I will see you in the next